So consider isomorphism between two fields, f and f bar. So C here is getting mapped to C bar here. So this isomorphism naturally extends to polynomials. So you have f of x, this will get mapped to f bar of x. So you have a polynomial here, c0 plus c1 all the way to cn xn. This lies in f of x. This will naturally get mapped to a polynomial in f bar of x. So c0 gets mapped to c0 bar, c1 gets mapped to c1 bar, cn gets mapped to cn bar, and nothing happens to x's. They remain as such. So this map here is faithfully carried out to this map here. So nothing much is done. So only the coefficients which are in the field are changed. And therefore you can define addition f1 plus f2 map to f1 bar plus f2 bar, and the multiplication here between g1 and g2 gets mapped to g1 bar times g2 bar. So in particular, say you have a polynomial p of x here which is irreducible, then the corresponding polynomial p bar of x will also be irreducible here. Now this is easy to see, you can prove it by contradiction. So say if p bar x factorizes like this, u bar times v bar, then p of x will also factorize as u times v, and this is a contradiction because you assume that p of x is irreducible. Now I want to make an important remark. So you have this field f of x, and then you modulo out by a irreducible polynomial. Since this polynomial is irreducible and this is a field here, this will become a maximal ideal, and when you do so, what you will get is a field f of a. So where a is a root of the polynomial p, that is p of a is 0. So notice that what do the elements of f of a look like? They're just fractions, f of a by say h of a. So the numerator is a polynomial and denominator is a polynomial. So the interesting thing here is that the inverse of h will also be a polynomial. So this you can write as f times h inverse. This is a polynomial, so this will become iso to fa. So that is just this field. So that is, you can take inverses of polynomials in such a field. So from round brackets here we have gotten to square brackets. So square brackets are precisely, instead of x we are writing a. So you're just polynomials. And to see this is easy. So since greatest common divisor of this irreducible polynomial, and any polynomial h is 1, you can rewrite this as hx vx plus p times u is equal to 1. So that is just by the property. So there are polynomials v and u which exist. You multiply like this, this will become 1. Now you evaluate this at a. If you evaluate this at a, p of a is 0. So this term will become 0. So this term becomes 0. And therefore you will have h of a times v of a is 1. So v of a is the inverse of h of a. So thus every polynomial h has an inverse. So this is nothing but f times v, and that's why you have multiplication of two polynomials. Wherever you have this fraction, this just becomes multiplication, and therefore you have a field. So this is a field. There are two ways of writing it. Now this is important to see because now you can just think of this f of a as just polynomials rather than as fractions. So now we want to work in such a diagram like this. So this is an iso here, and we want to extend it to this iso here. So that is, if you restrict this phi to just the base field, you will get this var phi. And these are just natural maps. This is the inclusion map, and this is our projection map. Similarly, here you have the inclusion map and you have the projection map. So here a is the root of the polynomial p of x. This p of x will get mapped to p bar of x, and the root of p bar of x is b. So obviously we have just seen this f of a is nothing but, and here it is f of p. So now everything is easy. You know that this a has to get mapped to b. So because this is how the polynomials are getting mapped. So you're taking care of the coefficients, and x's are not changing here. In this case the x is a, in this case the x is b. So let us see this more carefully. So say your degree of p is n. So the elements alpha of f of a, so any alpha you take here in f of a is of this form, c0 plus c1a to n minus 1, because degree is n. So you have n terms here. Similarly, alpha bar, which lies in here f bar of p, you have exactly like this. Instead of c0, you have c0 bar. So you have this addition you can define. So this alpha 1 plus alpha 2 here will get mapped to alpha 1 plus alpha 2 bar here, which is equal to alpha 1 bar plus alpha 2 bar. So trivially you can add and check. So this holds. Multiplication, again you have said two polynomials h1 and h2 here. Then these h1 and h2 will get mapped to h1 times h2 bar here. So say they are of degree less than n, then you can multiply them. But see, you have to modulo out with p of x. So you have to divide by p of x. So you will get some remainder. And then you have to plug in a. So this term will become 0 because a is the root of p of x. So you get h1a times h2a is r of a. Now we have to show that h1 bar of p times h2 bar of p is r bar of p. So because a is getting mapped to b, so this should make sense in multiplication also. But now you do not do much. You copy this entire thing right down here. Just put bar on both sides. You put bar on both sides, then this bar will factorize like this, just like here. This will become like this, and this will become like this. So obviously now you plug in b. Now you know the b is the root of p bar of p. P bar of p is 0. So you plug in b, and that will give you this equation. Plug in b here, this portion will become 0, and you get this equality right here. h1 times h2 evaluated b is r bar of p. So this makes sense. So what have we done? We have taken this var phi and extended it to phi.